Hello and welcome to our video on wave characteristics. We're going to be focusing on the measurable quantities associated with waves. Because even if you have two transverse waves, two waves that look like this, they could look very different based on their different measurable properties. We're going to label all these measurable properties in this set of notes. The first one, probably the easiest one for you to recognize, is the amplitude. You talked about amplitude before. You might not have called this type of wave a transverse wave in math class, but you certainly called it a sine wave. And you definitely talked about amplitude. The physics definition of this, might be a little different. I would define amplitude as the maximum displacement of the wave elements, the little pieces of the wave that are moving up and down in this case, from equilibrium. Informally, you can also think of this as the height of the wave. That's this right here, amplitude. Okay, from the equilibrium level to either the crest or the trough. So from the middle, we refer to this as, again, I said middle down here, but it's the equilibrium level to either the crest, which is up here, the peak of the wave, or the trough, which is down here. Okay, the units of amplitude depend on what the wave represents. If this is like a slinky and you're looking at this, then this might be the height of the slinky. You might say the amplitude is in meters. For a longitudinal wave, it's a little bit different. Amplitude is based for a longitudinal wave on the condensations or compressions and rarefactions. There's a good SAT word for you. Rarefactions just mean elongations. Longitudinal wave with a larger amplitude has more dense condensations and more spread out rarefactions. So I'm going to draw two examples of longitudinal waves, drawing the wave fronts, and you'll get to see what we mean by amplitude. So here would be like a condensation, then some spreading out parts, rarefaction, another condensation part. Okay, so we would say that the amplitude is from one condensation to the next. Okay, and the density of the condensation matters as well. This would be something with greater amplitude. Okay, so it's about how dense the condensations and how spread out the rarefactions are, if it's a longitudinal wave. Now, in most cases, the amplitude of a wave is proportional to the energy that wave carries, okay? Greater amplitude, more energy. So, for example, for sound waves, a greater amplitude, basically more spread out, basically compressions and rarefactions, means a larger volume. Don't get it confused with pitch or tone, or like how high the pitch is, the frequency. Bigger amplitude means more volume, more energy in it. For light waves, a greater amplitude means that the light is brighter. That doesn't necessarily transmit exactly to energy of a wave, but I do need you to know for light waves, if the amplitude is greater, that means the light is brighter. So amplitude is the distance or the maximum displacement of the wave from equilibrium. If you got a picture of a wave, you can find it by measuring how far the crest or trough is from the middle. Do not ever measure from the crest all the way down to the trough. That is not the amplitude. You talked about phase as well in math, although you maybe didn't talk about it the way that we're going to talk about it. 2 points that are on a wave will be in phase with each other if two criteria are met. Their displacements from equilibrium are equal, and if those 2 points, if the wave was moving, would be moving in the same direction. Okay, so I'm going to draw some shapes up here around different points on this wave. I'm going to put a circle here. I'm going to put a square up here. I'm going to put a triangle right here. I'm going to do the same thing here. Circle, square, triangle. The reason I've done this is to illustrate for you what points are in phase. The points in the above picture that have the same shape on them are in phase. So circle and circle, square and square, triangle and triangle. In each case, their displacements from equilibrium are equal. Circle and circle, they're both at equilibrium. Triangle and triangle, they're both at equilibrium. Square and square, they're both at the crest. If I had maybe, I don't know, like a diamond shape down here, and if this wave continued, I would have another diamond shape over here, and those points would be in phase. And these points are moving in the same direction. Let's assume the wave is traveling this way. So the circles, let's see, the next thing that this circle is going to encounter, if this wave is moving to the right, is this trough. You can imagine if this wave extended back farther, then this circle would also experience a trough. So these circles are both moving, you could think, down. These wave elements right here, they would be moving down at this point. The squares, same thing. They're about to start to go back down the crest if the wave slides this way, and therefore they'd be moving down. The triangles, on the other hand, this crest is about to move over here, this crest is about to move over here, the triangles are both moving up. They are all in phase. What you cannot say is that the circle is in phase with the triangle. The triangle, like we just said, if the wave is moving to the right, is about to go up this crest. The circle is about to fall down into this trough. They are not in phase, even though their displacements from equilibrium are equal. Okay? So, we'll come back to that in a second because 2 points that are in phase have another interesting characteristic. Phase is measured in degrees. If points are in phase with each other, then they are 0 degrees apart or 360 degrees apart. We're linking it back to kind of like a circle. If you go all the way around the circle, you've gone 360 degrees around that circle. If you go through one full wave, then you've gone 360 degrees as well. So you either say they're 0 degrees apart or 360 degrees apart. If you have points that are exactly out of phase, such as our circle and our triangle, you would say that they are 180 degrees apart. Another example of out of phase, exactly opposite each other on the wave, would be a square and like this trough down here. Now, phase really comes into play when we talk about wavelength. This is another way to understand phase differences. I think this kind of fits together very nicely. If 2 points on a wave are in phase, I'm going to move this down just a little bit. If 2 points on a wave are in phase, then the physical distance between those points is the wavelength, and that would be measured in meters. So let's look at this picture again. The circle and the circle, they are in phase with each other. And look at that. We have an arrow that stretches from the circle to the other circle. This actually demonstrates to us the wavelength. Okay? We could also have a wavelength from the square to the square and the triangle to the triangle, points that are all in phase with each other. Notice that you could physically measure what that distance is in meters. So you can think of a wavelength as one complete cycle of as the distance between 2 points that are in phase. You can also think of a wavelength, and I like to do this, as the length of one complete cycle of a wave. Okay? The total distance for the wave to start here, go all the way down, and then all the way back up. That's one complete cycle. Or start here, up, down, up. This is not one complete cycle. Matter of fact, this is exactly half of a cycle. This is half of a wavelength. So another way to think about this, points that are in phase are one wavelength apart. You could say that they're 0 degrees or 360 degrees apart. You could also say they're one wavelength apart. Points that are exactly out of phase are said to be 180 degrees apart. You could say that they are a half wavelength apart. Okay. The symbol for a wavelength is this kind of funny looking letter here. It looks kind of like some people have said giraffe, some people have said like an upside down Y. It's called a lambda, L-A-M-B-D-A. It's a Greek letter. I think the best way to draw a lambda is to draw a 7, and that 7 has a little leg sticking out to support it. And we should talk about wavelength for longitudinal waves, and I need to apologize. because I screwed up the beginning when I said that this is the amplitude. This is not the amplitude. The amplitude for a sound wave or for longitudinal waves, let's cross that off, would basically be how compressed, how close together these wavefronts are, how spread apart these are. Okay, how compressed these are, how spread apart these are. That would be the amplitude of a longitudinal wave. On the other hand, what I drew in was actually the wavelength. Okay, so for a longitudinal wave that looks kind of like this, see, here's our wavefronts. Here's an area of compression. Here's an area where they're spread out a little bit more, rarefaction or elongation. This distance right here, not that whole thing, this distance right here between successive areas of compression would be a wavelength. Okay, I apologize for up here. I mixed up amplitude and wavelength for longitudinal waves. The distance between compressions or the distance between centers of the spreading would be a wavelength. The amplitude up here is not what I was trying to draw in. The amplitude would be how close together these are and how spread apart these are. Okay? We've got to talk about period, frequency, and speed. Period and frequency are very closely related. As you can see from our reference tables, by the way, this is page 5 in the reference tables, the period is given the symbol T. And the definition of period is the time required for one complete vibration of the wave to occur, symbolized by T. Kind of makes sense. Lowercase t is for time, uppercase T is for period. A period is just an amount of time, the time required for one complete vibration of the wave. If you go back to the front and we look at this picture, then that also means if this had time on the x-axis, then this line that says wavelength, well, it could also symbolize the period. Imagine that you were graphing like the height of the wave versus time. The time from here to here would be the period. If you're graphing instead, like if this is a picture of the wave, like this is the height and this is the x distance, then this would be the wavelength. Again, you have to know what you are graphing, just like everything else we have done in this class. So period is a time required for one complete vibration or one complete cycle of the wave to occur. The symbol is capital T. Frequency is related, but it's not the same thing. It is the number of vibrations or cycles that occur per unit of time. You have dealt with frequencies before. When you go to the doctor and they take your heart rate, that is measured in beats per minute. A heartbeat is a cycle that repeats over and over again. Hopefully it does, or else you got bigger problems. So it's in beats per minute, number of cycles per unit of time. RPM, if you look in your car, you're looking at like an engine or something, you look at revolutions per minute. That's also a frequency. It's how many times the engine turns over per minute. Okay, I have this. Okay, frequency is commonly measured using seconds. That's a little misleading. Frequency is not measured in seconds. The unit is hertz. The symbol is capital HZ, and the unit hertz is equal to 1 over seconds. Okay, so we're just going to get rid of this. Frequency, I don't like saying this, frequency is measured in seconds. We use seconds to measure. I'm screwing it up. Seconds are involved in the measurement, but it's not measured in seconds. It's measured in 1 over seconds. And frequency is lowercase f. So period and frequency are really closely related. People mix them up all the time. They apply not only to waves, but to any motion that is periodic, anything that repeats. Okay? So think of, for instance, like a wheel going around and around and around, or a wave. That is repeating, or literally anything else, beats per minute, that can work as well. So let's see how they're related. If there are 2 cycles of a wave that occur per second, what is the period of the wave? If 2 waves occur per second, that's telling me the frequency because it's the number of waves or cycles per second, a unit of time. So that's the frequency. If 2 happen every second, how long would just 1 take? Well, if there's 2 per second, then that means that 1 would just take half a second, because then 2 would take a full second. So that means the frequency is 2 hertz. The period is 0.5 seconds. Let's do a related problem. A wave has a period of 0.2 seconds, 0.2 s, What is the frequency? Well, if one full wave happens in 0.2 seconds, then in 0.4 seconds, you get 2 waves. In 0.6 seconds, 3 waves. In 0.8 seconds, 4 waves. In 1 full second, there would be 5 waves. 5 waves in 1 second. 5 waves, cycles per second. The frequency would be 5 hertz. Now you should notice something about these. Look at these numbers, 2 and 0.5. Watch what happens if I multiply them. 2 times 0.5. 2 times 0.5, I get 1. 0.2 times 5, I get 1. It seems to me that if you take the frequency and you multiply by the period, you get 1. And that's true. Now, no one writes it like this. Instead, we divide both sides by f, and we write it like this. T equals 1 over f. What this tells me, that equation's right here, by the way, T equals 1 over f. What this equation tells me is that period and frequency are inverses of each other. They are not the same thing. They are inverses. One is measured in seconds. One is measured in cycles per second. Okay, you can think of period as seconds per cycle. How many seconds does it take for one cycle to happen? Frequency is how many cycles can happen in 1 second. They're closely related, but they are not the same thing. We can use that to figure out this question right here. If a bike wheel goes 1 complete rotation every 0.12 seconds, how many times does a bike wheel go around per second? 1 rotation in 0.212 seconds, that's the period, okay? If that's the period, we're looking for the frequency. How many times does it go around per second? Clearly it's more than just 1 because it happens many times per second. So if I have T equals 1 over F, notice that if I multiply both sides by F and then divide by T, I get this equation. The frequency is 1 over the period, okay? These equations are basically just the inverses of each other. It's the same equation, but we've just swapped where the T and the F are. If the period is 0.12 seconds, I take 1, I divide by 0.12. I find that the frequency in this case is 8.33 hertz. 8.33 cycles per second, okay? 1 over seconds is hertz. That basically means cycles per second. That means the bike wheel goes around once every 0.12 seconds. It's going to go around about 8 1/3 times per second. Okay, frequency and period, I know they're a little confusing. They seem so similar. They are, but they are different things. You've got to make sure you have those straight. As far as some useful some waves that we're going to use a lot and what the frequency tells you. For a sound wave, the frequency tells you what you would call the note or the pitch or the tone, basically how high the sound is. Okay, is it low? Is it a low sound or is it a high sound? For light, and this is really interesting, the frequency actually tells us the color. Okay, our brains interpret frequency of light as color. That's really neat. Our last wave characteristic that we're going to talk about is speed. Okay, wave speed. Since waves travel real distances, we can measure wave speeds, which are different for each wave. It actually depends on the medium. It depends on what they're traveling through. The formula for calculating a wave speed is this. V for speed equals F times lambda, frequency times wavelength. Now that seems like a weird equation. How are frequency and wavelength, how do you multiply those together and get the speed? This, honestly, this bothered me when I was taking Regents. I had to really think about this to have it make sense. Here's what I came up with. Imagine that you're standing in the water, and let's say that there's some waves coming at you. The waves are all separated by, let's say, 2 meters, okay? And let's say that, and this is a little unrealistic, 4 waves are hitting you per second. So if the wave crests are separated by 2 meters, that's the wavelength. And if 4 waves hit you per second, notice the per second, that's the frequency. So imagine that you're just getting hit by a wave. So that wave is in the same position as you. What's going to happen is that wave is, by the time the next wave hits you, that first wave is 2 meters farther away. It's 2 meters from you. Okay, it's 2 meters past you. And then the next wave hits you. That first original wave is 4 meters past you. And then the third wave hits you. It's now 6. The original wave is now 6 meters away. When the fourth wave hits you, that first wave is now 8 meters away. Okay? And remember, we said 4 waves hit you per second. So every quarter of a second, another wave hits you. So if 4 waves have hit you, then that first wave is 8 meters away. Then that wave has traveled 8 meters in 1 second, 8 meters per second. How can we get 8 meters per second? We take the frequency, 4, multiply by 2, the wavelength, and we get 8. So that one's a little bit of a struggle. Sometimes you really have to visualize that one, and we'll do things in here to help with that. Okay, and so here's something that always gets me, and I don't understand. I don't know if this just isn't taught in elementary school. I thought that this was just common knowledge. But sometimes, like every year, someone tells me that lightning comes because of thunder. It is totally not true. It's the other way around. You see lightning before you hear thunder. If you hear thunder and then see lightning, well, guess what? You're looking at another lightning. You missed the first one, okay? We always see lightning before we hear thunder because light waves travel much, much faster than sound waves. And we can see this by looking at the reference tables. On the reference tables, at the top, we see the speed of light in a vacuum, which basically means empty space. By the way, it's got the symbol C, is 3 times 10 to the 8th. That is 300 million meters per second. Speed of sound and air at STP, standard temperature and pressure, chemistry reference, is only 3.31 times 10 to the second meters per second. 10 to the second is 100. 3.31 times 100 is 331 meters per second. 300 million versus 331? Not that close. So speed of light in a vacuum is 3 times 10 to the 8th meters per second. Speed of sound in air is 3.31 times 10 to the second meters per second. And these are different in every material. These speeds. The speed of light is different for every material light could pass through. It's actually slightly different in air, it's different in water, it's different in glass, etc., etc. Different in each medium. It's lower in denser materials for light. Okay? Light doesn't travel as fast if it's going through something dense. Sound is similar in that it's different in each medium that sound can pass through, whether that's air or water or steel or something like that. But sound is weird. Sound actually travels faster in denser materials. And that's because of how sound waves propagate. You can't have sound waves if you don't have a medium. So the closer together that the medium is, the more tightly packed the atoms are, the quicker they can knock into each other and transmit that sound wave. Real quick, we'll just do some examples showing how to use that V equals F lambda equation. It's not a replacement for V equals D over T. It's simply another way of expressing speed if we're dealing with waves. A sound wave in air has a frequency of 440 hertz. What's the wavelength of this note? So we're looking for lambda. We have the frequency. Sound waves, we know, travel at 3.31 times 10 to the second meters per second. That's 331 meters per second. I'm just going to write that. Equals the frequency of 440 hertz, which is some relevance in music, but I can't remember what it is. It's like concert A or C or something like that, times lambda. We can actually figure out the physical size of this wave. If this wave occurs 440 times per second, that's what hertz means, how many times the wave occurs, the cycle repeats per second, and it travels 331 meters per second, we can actually figure out how big that wave is. 331 divided by 440. The wave is 0.752 meters, a little over 3/4 of a meter long. That is the distance between, let's say, crests of that sound wave. Okay? Kind of interesting. All right, a type of green light has a wavelength of 5.89 times 10 to the negative 7th meters. What is the light wave's frequency? Well, V equals F lambda. This time we're dealing with light. Light has a speed of 3 times 10 to the 8th meters per second. We want to know the frequency. We know the wavelength is 5.89 times 10 to the negative 7th meters. By the way, that is so small you can barely imagine it. 3e8 divided by 5.89 times 10 to the negative 7th. The frequency is 5.09 times 10 to the 14th hertz. Think about what that means. That means that that light wave, that electric field, oscillates, because light waves are made up of electric and magnetic fields. That wave oscillates. It goes through basically 50 trillion cycles per second, and your brain interprets that as green color. That's crazy. That is so cool. Last example, and this is going to show you that we can still use V equals D over T when we're dealing with waves, but it's just not as common. Lightning strikes 3 kilometers away. Find the times for the light and sound waves to reach you. Well, if it's 3 kilometers away, that's not a wavelength. That's not distances between like crests or anything. That's just literally a distance. We know how fast light moves, so we can find the amount of time it takes to reach us. 3 times 10 to the 8th meters per second for light equals 3 kilometers. Let's see, that's 3,000 meters. Need to have that in meters. Times t. We're going to multiply both sides by t and then divide both sides by 3 times 10 to the 8th. So I do 3,000 divided by 3e8, and I get 0.00001 seconds. That's how much time it would take the waves to reach you if lightning struck 3 kilometers away. That's like, I'm at the school right now, that's like if lightning struck down at Riley's. It would take 0.00001 seconds for that light to reach me. Looks instantaneous, it's not quite. On the other hand, the sound. The sound's got to travel the same distance, but it travels at a much lower speed, 331 meters per second. It's got to go 3,000 meters. Clearly, this is going to take much more than 1 second. We're going to do the same thing. 3,000 divided by 331. It would actually take the sound about 9 seconds to reach you if lightning struck at Riley's and you're sitting at the high school waiting to hear the sound. Lightning occurs before thunder. The light waves from the lightning reach you almost instantaneously. The sound comes much, much later. What I need you to take away from this is that light waves travel much faster than sound waves, okay? But overall, you should understand how to use this equation to measure the speed of a wave. Speed of a wave is equal to the frequency of the wave multiplied by the wavelength, okay? We're going to talk about we've talked about the general nature of waves. We talked about how to do all the measurable things with waves. Now we're going to get into the effects of waves, things that waves can do which have kind of neat applications for us.